Hello, my name is Erik Pruit. I'm a methodologist at Delft University of Technology. This week is about modeling techniques. In this web lecture, we will look at one of these techniques, the system dynamics modeling and simulation method, what it is used for, how it is used, and what is specific about system dynamics. We will also briefly look at two examples. So, what is system dynamics? It's a method for modeling and simulating dynamically complex issues or systems characterized by feedback and accumulation effects. I will come back later to that. So, what is system dynamics used for? Quantitative system dynamics modeling is used to model systems and issues and to simulate their behavior over time. Models can then be used to experiment in a virtual laboratory, and as such, system dynamics models are also extremely useful for model-based policy analysis and for adaptive policy design. This can be used to identify the root causes of problems, identify adaptive policies to solve problems at the root, and to test the effectiveness of policies across a very wide range of assumptions. So, what are the application domains? Well, system dynamics is used for many complex social, technical, and policy problems. For example, in health policy, based on a system dynamics study by KidRisk, the WHO was convinced that polio should be eradicated worldwide, and the Gates Foundation decided to co-fund the eradication effort. System dynamics models have influenced and driven energy policies and infrastructures in the US and elsewhere since the 1970s. And the same is true for resource dynamics and management from the moment the first Limits to Growth study commissioned by the Club of Rome was published in 1972. In line with the follow-ups of the Limits to Growth and the growing concern that pollution, more than finite resources, poses severe limits to growth, the system dynamics field also shifted more and more towards environmental policymaking. For instance, the flight simulators and serious games developed by Climate Interactive help climate change policymakers understand the impact of climate change policies. System dynamics has also been used since Jay Forster's urban dynamics study for studying urban dynamics and policies. Recently, a system dynamics model of the relationships among many core city systems was developed for the Smarter City project of the city of Portland, Oregon, to better understand urban dynamics and to identify opportunities to become a smarter city. System dynamics is also used for education and innovation. For example, a system dynamics model of the Business Higher Education Forum has recently been used to study how President Obama's goal of 1 million science, technology, engineering, and mathematics graduates could actually be met. System dynamics is also used for strategic planning and all sorts of business dynamics problems. Think about books like Business Dynamics or Strategic Management. System dynamics models are also used for integrated risk capability assessment and critical infrastructure protection. And finally, system dynamics models are used for many socio-economic and public policy issues, such as societal aging. So, how are system dynamics models made and used? In other words, what does the system dynamics process look like? As you can see from this picture, the system dynamics process is very iterative and interactive. Problem owners and stakeholders are involved in many, if not all, stages of the process. In fact, it all starts from the mental models of problem owners and stakeholders, and from this starting point, system dynamicists first distill conceptual models. These conceptual models are then turned into fully specified formal models, which are simulated, tested, used. Often the purpose is to design adaptive policies and to test their robustness using these models. But in many cases, the aim is also to generate new insights and improved understanding of the problem. So, what do system dynamics models look like? Let's have a look at the technique. This might be a difficult part, but if you get confused, just have a look at the additional resources we included in this MOOC. Two types of diagrams are often used in system dynamics. The first type, stock flow diagrams, are mainly used to build simulation models. Stock flow diagrams focus, as suggested by the name, on stocks and flows, which are two types of variables. Stock variables are accumulations of all inflows minus all outflows over time. And the net flow actually determines the behavior of the stock over time. So mathematically speaking, stock flow structures are differential or integral equations. Apart from stocks and flows, constants and parameters are also included in these models. And auxiliary variables are included to build models that closely correspond to the real-world system. Auxiliary and flow variables often contain very specific functions, such as nonlinear graphical functions or delay functions. Direct causal relationships between these variables are indicated with blue causal links. Note that the flows are causal links too, and also note that variables need to have a real-world meaning, correspondence, and that all units need to be consistent. Then, if a model is fully specified, it can simulate behavior over time. And this type of representation is really good for building models and communicating stock flow structures, but it's not really appropriate for thinking in terms of feedback loops or communicating important feedback effects. For this purpose, system dynamicists use causal loop diagrams. These show causal links between the main variables, the polarity of these causal links, the feedback loops, and the polarity of these feedback loops. A positive causal link from A to B either means that A adds to B, if B is a stock variable, or that a change in A causes a change in B in the same direction. And for a negative causal link from A to B, one says that A subtracts from B if B is a stock variable, or that a change in A causes a change in B in the opposite direction. A feedback loop consists of two or more causal links between elements that are connected in such a way that if one follows the causality starting at one element in the loop, one eventually returns to the first element. There are actually two types of loops. A feedback loop is called a balancing loop if an initial increase in variable A leads after some time to a decrease in A, but also if an initial decrease in A leads to an increase in A. In isolation, such feedback loops generate balancing or goal-seeking behavior. A feedback loop is called a reinforcing loop if an initial increase in variable A leads after some time to an additional increase in A, and so on. And if an initial decrease in A leads to an additional decrease in A, and so on. In isolation, such reinforcing feedback loops generate reinforcing behavior, exponential behavior, for instance. But feedback loops hardly ever exist in isolation. Feedback loops are often strongly connected, and their relative strength changes over time. Complex system behaviors often arise due to such shifts in dominance between different feedback loops in the same system. When dealing with feedback loop systems consisting of multiple loops, it is hard to derive the behavior of the system without simulation. So let's gradually transform the previous stock flow diagram in a causal loop diagram. The first step would be to turn the flows into causal links. An inflow into a stock is actually a positive causal link from the flow variable to the stock variable. But an outflow out of a stock is actually a negative causal link from the outflow variable to the stock variable. The higher the outflow is, well, the lower the stock variable will become. If we further transform stock flow diagrams into causal loop diagrams, we need to add the link polarities, identify the feedback loops, and derive the loop polarities. In this case, we would end up with a reinforcing loop with a delay and a balancing loop. And depending on which loop is dominant and whether dominance shifts between these loops, the feedback loop system could generate several modes of behavior. For example, exponential growth if the reinforcing loop remains dominant, or S-shaped growth if the balancing loop takes over after some time. So what's specific about system dynamics? Well, system dynamics models are largely endogenous theories. That is, model boundaries are chosen such that all the important feedback loops are within these boundaries. System dynamics models are also rather aggregated. Stock variables are often used to group rather homogeneous individuals or items. This also means that we need to make sure the aggregation assumption holds in order to be able to use system dynamics modeling. If the aggregation assumption holds, well, then system dynamics has an advantage over less aggregated methods. System dynamics is therefore most useful for studying the long-term big picture. As already mentioned, system dynamics models are integrated numerically to generate the behavior over time. System dynamicists assess and interpret the resulting trajectories over time as general modes of behavior. For example, oscillatory behavior, S-shaped growth, overshoot and collapse. In case of undesirable modes of behavior, system dynamicists actually analyze which structures need to be changed or added to change the undesirable modes of behavior, for example, exponential growth, into more desirable modes of behavior, for instance, an S-shaped curve. So outcomes are not interpreted as precise predictions. Outcomes are really general foresights at most. System dynamicists are actually far more interested in improving our understanding and changing faulty mental models and generating general policy insights than generating predictions. As such, system dynamics models are essentially tools for thought. More reflection beyond the model is also hugely important in the system dynamics process. So, let me give you two examples now. A very simple example first, and then a more advanced. Let's make a very simple model about the electrification of the European car fleet between the years 2000 and 2100. Say, at the start, there are nearly 100 million conventional vehicles and only 2,000 electrical vehicles. Owners of electric vehicles stick to their electric vehicles, and at the end of the average lifetime of a conventional vehicle of, say, 10 years, conventional vehicle owners may consider buying a conventional vehicle or an electric vehicle. Suppose that the electrification process depends on some sort of incentive. Say, this incentive makes electric vehicles 5 times more attractive than without this incentive between 2005 and 2015. Simulating this very simplistic model, we obtain the S-shaped growth of the stock of electrical vehicles following the electrification process displayed below. The second example relates to material scarcity, mining and recycling infrastructures. The model displayed here is a bit bigger than the previous model. It consists of a demand submodel, a supply submodel, an extraction submodel, and a recycling infrastructure submodel. These submodels are all linked together, although it doesn't show in this picture. The model was made with mineral metal scarcity experts and used to develop scarcity scenarios. The model actually generates very interesting dynamics. The blue lines on the left and the right give an indication of mineral metal abundance and scarcity. In the simulation, there are first some temporary periods of scarcity, and after that, after 2030, scarcity becomes chronic. Changing a few assumptions leads to even more interesting dynamics. These and other scenarios can then be used to design and test policies and strategies for different stakeholders. So, system dynamics is useful for modeling complex social technical systems and simulating dynamically complex behaviors over time. Without system dynamics or other simulation techniques, this is almost impossible. Here, we briefly looked at the basics of system dynamics. From here on, we recommend you to work through various ebooks, books, online resources, do supervised projects, take advanced courses, and so on. After that, you are ready to make and use your own system dynamics models and combine system dynamics with other methods. And then the fun really starts. Enjoy.